Okay, welcome to the third week's online lecture. You know, the last week was a little bit difficult week because you had to study 2 chapters in a week. But from this week, for the time being, we will study just 1 chapter per each week. So let's relax and get back to the lecture. So in the last lecture, we studied the electric field and the electric field lines. And we studied the electric dipole and its potential energy in a uniform electric field. And we also learned what electric flux is and also what Gaussian surfaces are. And finally, we learned how to use the Gauss law to calculate an electric field. Okay, and in this lecture, we will introduce the concept of electric potential and learn how the electric potential is related to the electric field and calculate the electric potential for simple cases of charge distributions, and also define the notion of equipotential surfaces, and finally study the relation between equipotential surfaces and electric field lines. So before learning what electric potential is, let's try to remember the potential energy that we have learned in the spring semester. The electric potential and potential energy anyway sounds very similar, right? So take a look at the figure on the right hand side. Here the hand is throwing the tomato up high, and then tomato goes up and is falling down. And during this motion, we are not actually considering the work done by the hand, but actually done by the gravitational force. So we have learned in the spring semester that the change in potential energy is equal to the negative of the work done by an object, done on an object by a conservative force, in this case the gravitational force, to move it from one position to the other. So for example, when this tomato is going up, you see that it's moving opposite direction with respect to the gravitational force. So therefore, the work done is actually negative. So therefore, if we put another minus, the potential energy actually becomes plus, larger than 0. Okay. And when the tomato is falling down, now the displacement factor is actually parallel to the gravitational force. Therefore, the work done becomes positive, and then the gravitational potential energy, the change in gravitational potential energy, will become negative, which means the potential energy is decreasing. Okay, so just likewise, any potential energy or is change suggests that the object is in some kind of force field, right? And the situation of this Coulomb force is actually the same. Suppose there is a positive charge here, and then it's giving off this electric field, and then if you have another positive charge very close to it, then there will be a Coulomb force which is working like this. Again, it's the same situation. This charge is in a force field. And then suppose this charge is moving from initial position to the final position. And in this example, you can see that, again, the charge is moving along the opposite direction with respect to the Coulomb force. So therefore, during this motion, the work done by the Coulomb force will be negative. So therefore, the potential energy of this object or charged object will increase. So that is the situation. So let's see how we can actually quantitatively calculate this change in potential energy. So this is what we are doing. Just like we have done for the gravitational force, what you have to do is you are integrating this force through the displacement, but eventually put minus sign here. This is what we are doing. And then we already learned what the Coulomb force must be is K multiplied by 2 charges, large Q and small q, divided by their distance square, which is r square, and then we are integrating by dr. And then you see that if you integrate 1 over r squared, then what do you get? is minus 1 over r. So because we already have a minus over there, we actually get 1 over r, right? And then you get 1 over r, and then you are integrating from say r(I) initial position to r final position, okay? And then this will be what you get, and then the rest are just constant, right? Okay. So simply, this is how you calculate the change in potential energy due to the Coulomb force or electric field or anything of this kind. And then we know that in the gravitational case, we learned that, well, even though in potential energy, what matters is only the difference or the change, but then it will be very convenient if you can find a place or position where potential energy may be referred to as being zero. In the case of gravitational force, the surface of the Earth is the place where it's convenient to put the potential energy to be zero, right? And similar to that, if you can find a position where this we can put the potential energy to be zero, then instead of differences, we can actually talk about the absolute value of the potential energy. So where would that be? Is it just over here, just like in the gravitational force? No, actually not. The reason it is not a good idea to put the potential energy to be zero at the surface of this charge is because the Coulomb force will be very strong, so then it's almost becoming infinite. But in contrast, it will be very convenient if you choose one position where the Coulomb force becomes zero. Then that is the place where you may want to choose as a reference point or 0 point of the potential energy. Where is it? It is in fact the position where the distance becomes infinite. If these two charged objects are infinitely far away, effectively there will be no Coulomb force, of course mathematically, right? So that is the place where we'll put the potential energy to be zero. Then the above equation over here, what does it happen if you put this to be the infinite? Then the total value will become just zero, right? Okay. And then now instead of saying Rf, which is a final position, let's just replace with R. So we are expressing the potential energy just simply as a function of position, which is R. So this is what we get. Okay. Now this is how we, starting from the same idea of the gravitational potential energy, this is how we express the potential energy due to the Coulomb force, and then also try to find where is the best place to put the potential energy to be zero, and then get the idea of absolute value of the potential energy. Okay. And what is electric potential? You know, the electric potential sounds similar to the potential energy, but it is not an energy. Okay, so try to remember why we have previously introduced the electric field. While the Coulomb force was easier to understand because Coulomb force was something we can directly feel, the electric field was in fact more convenient because it could be defined for each charge and independent of the test charge, right? So we are taking a very similar approach and try to remember the definition of the electrostatic potential energy. And you know, it requires the two charges to be defined, and this is very similar to the case of Coulomb force. So therefore, similarly to the process of defining electric field, we now introduce electric potential, which can be defined for each charge and independent of the test charge. Okay, and how do we do that? We define electric potential by dividing the electrostatic potential energy by the size of the test charge. Okay, take a look at the equation here. So we are dividing the electrostatic potential energy by the test charge, and then get the electric potential. Okay, and then what is this minus W infinity? Well, if you do not remember, please go back one slide, and then there will be an explanation. Basically, what it means is the work done by the Coulomb force when the test charge was moving from infinitely far away to a certain position. Okay. Okay, and we can also summarize that in other words, the electric potential is the electrostatic potential energy per unit charge. Okay, that's what it is. And remember that in the case of potential energy, it was the difference that mattered. So similarly, you know, the electric potential is not exactly the same as the potential energy, but it is in fact very similar in many respects. So also for electric potential, the difference is very important. So we now again try to consider the relative changes or the difference in the electric potential. So here we are expressing delta V, which is the difference between VI and VF. And then what is VI? So VI will be the electric potential at this location. Before we consider that the test charge is located at this position, but in the case of electric potential, now we actually disregard or forget about the test charge. So therefore, without test charge, the electric potential coming from this positive large Q here will be the VI here, and then it will be VF here. So the difference is written as delta V. Okay, and then how do we actually calculate VI and VF independently? Of course, go back to the definition, and VI will be the UI divided by Q naught, which means that the UI will be the electrostatic potential energy of the test charge at this location, and then UF will be the electrostatic potential energy of the test charge at this location. So eventually their difference will be delta U, and then if you divide it by Q naught, which is a test charge, then you again get the electric potential difference. Okay, and then what is this minus W? Okay, again the W will be the work done by the Coulomb force when a test charge is moving from the initial position to the final position. And then if you put minus here and then divide it again by the test charge, then you get the electric potential difference. Okay.